Lots of people ask themselves whether it's really necessary to add EEG to MEG, get your hands dirty, and fix these electrodes and everything. Of course, that's only if you have the luxury to have access to an MEG system. Similarly, if you have an EEG system and you ask yourself, well, should I actually do this with MEG? Should I look for somebody who can give me access to an MEG system? Then you need to know, what are the differences between EEG and MEG, and maybe it's even the best of all worlds to combine the two. So in order to look at that, I'll just put a few slides together here. Some of them I showed before. Let's just remind ourselves that EEG and MEG do measure effects of the same sources, so these primary currents here, but they measure different aspects of them. So primary sources produce these volume currents, and they produce electric voltage differences on the scalp. Both primary and volume currents produce magnetic fields. We measure them with MEG. So this already suggests that we measure different types of information, which might be useful for different purposes, but maybe together, you will actually get the most information out of it. This is not quite accurate, actually, so I just want to highlight again that actually the currents obviously are not homogeneous around the whole head. They decrease with distance, and especially they're attenuated by the skull, and that has quite serious consequences for EEG. So unfortunately, EEG looks at a very blurred version of these signals. MEG is mostly influenced by magnetic fields from volume currents or currents around the primary source, including the primary source. But that has more practical consequences for head modeling, for example, which we talk about in a different session. We also already talked about the different sensor types. So there's MEG and EEG, but even MEG is a bit more complex. So you have magnetometers, axiogrameters, planar gradiometers. And it's important to remind ourselves that every sensor has a different type of sensitivity profile. So if you imagine that this is a sensor and underneath is the brain, then these different positions in the brain, the sensor has different sensitivities with respect to location. For example, it usually decreases with distance to the sensor, but also with respect to orientation. So in this case, with a simple magnetometer, if this dipole would point directly towards the sensor, this sensor would not pick up any signal from this dipole. And when it's tangential like this, then it has maximum sensitivity. And interestingly, with magnetometers, if the dipole is hiding directly underneath the magnetometer, it wouldn't pick up anything either, because then the magnetic field above it would be zero. And planar gradiometers have another sensitivity profile. And then EEG again has a different sensitivity profile. EEG is mostly sensitive to dipoles that point towards the electrode. So this already suggests that yes, all these different sensors pick up different types of information, but importantly, also every sensor type is insensitive to certain types of sources, like here, a source directly underneath. So you definitely need a combination of sensor types to get as much information as you can. We saw this slide already. So this presents some differences between MEG and EEG in cartoon fashion. So imagine the head is a sphere. Then both MEG and EEG pick up signals from tangential sources, that means parallel to the scalp or the skull surface. For radial dipoles pointing towards the skull or the scalp, MEG is insensitive, but EEG can still see them. A special case of a radial source is a source directly in the center of the brain. So EEG can still pick something up, but MEG can't. That also means that the deeper the source is, the more radial it is. That means MEG has probably less sensitive to deeper sources than EEG. And then there are some of these more complicated source distributions, which also illustrate simply that EEG and MEG are sensitive to different types of sources. So you will just get a different type of information depending on whether you use EEG and MEG, which should also suggest that if you combine the two, you get as much out of your data as possible. And this, I think, is illustrated by two studies that I would like to highlight here. So especially if you're new to EEG and MEG, then I think it's actually instructive to look at those. So in this case, they looked at so-called sensitivity maps. So if you're using a particular software package, then maybe you should check whether you can actually compute that with for your own data. I think it's always useful, educational to look at that. So if you put dipoles at every vertex on your cortical surface and you compute the signal from a dipole with unit strength, and then you can visualize that for every location on the cortical surface as a signal to noise ratio with respect to some arbitrary noise level, and this here is expressed as decibels. Then you get an idea of which areas you're most sensitive to and which areas you're least sensitive to. So in this case, yellow and reddish colors mean high SNR, high sensitivity, bluish colors mean low sensitivity. And for MEG alone, we can confirm what we already said before. The deeper you go, the less sensitive you are. In fact, it drops off quite steeply here. So within a few centimeters, if you go down a few centimeters into the cortex, you have much lower sensitivity than when you're close to the sensors. With EEG, this is less pronounced. So yes, you do lose sensitivity if you go into deeper brain areas, but this is less steep than for MEG. It also looks a bit more speckled for MEG. So you can see some of these blue stripes here, even when it looks close to the sensors. And this is because these are probably the tips of the gyri. So here you see the curvature of the cortex. That means these sources are radial, so they point towards the sensors. And the head is not a complete sphere. So in a realistic head model, their amplitudes will not be completely zero, but there will be much lower sensitivity to these sources, much lower than for the other sources. So that explains the decrease of sensitivity with depth, as well as to some of these sources here in the more superficial areas. And with EEG, it's actually the other way around. So radial sources, if they point directly towards the electrodes, you have high sensitivity. This probably explains these stripes here. Another observation you can make here, EEG seems to be less sensitive to these more anterior sources, anterior temporal, frontal sources. This is a little bit, I think you can also see a little bit of that here in the MEG. It's not necessarily a general property of EEG or MEG that they are less sensitive to frontal sources. It also depends on where the sensors are, of course. If you sit in the MEG helmet and you lean back, then your frontal lobe might be further away from the sensors than your visual cortex, so you might compensate for that a bit. And similarly with EEG, you might put more electrodes in the front of to the front of the head to increase your sensitivity here. So of course, sensor coverage matters as well. It's not necessarily just the physics of EEG and MEG that matter. Importantly, if you then combine the two and you take the maximum signal to noise ratio, obviously not surprisingly, then you get a nicer distribution here, a bit smoother. You cover more of the cortical surface. Depth sensitivity is better than for MEG alone. So yeah, so if you combine the two, you get the best of both worlds in this representation anyway. But what we are not taking into account here is that we are only looking at dipole sources. So these are in basically every location, every vertex, we assume an infinitesimally small source. I mean, that's what the dipole represents. We do not take into account the spatial extent of sources. And that's what they did in this analysis. So here they started also using dipole sources as before, and they get a very similar pattern as before. In this case, color coding is different. Blue means that EEG is more sensitive, and yellow means that MEG is more sensitive. And you can see that this is basically a summary of what we just talked about. MEG is more sensitive to most of the superficial brain areas closer to the senses, apart from maybe the radial bits here, some of these stripes. And in depth, EEG is more sensitive. I mean, there's most dramatically visible here. So as soon as you go 1 or 2 centimeters below the surface, EEG is more sensitive than MEG. But look at what happens if you use spatially extended sources. So not dipole sources, but actually 10 little disks of 10 millimeter radius. So now EEG becomes more sensitive in a larger area of the cortical surface, not just in depth. And if you then extend these sources even further to 16 millimeters radius, most of the cortex actually prefers EEG compared to MEG. And why is that? Well, I mean, if you think a little bit about, distributed sources as dipoles around, for example, a cortical sulcus here. So imagine this is active more or less homogeneously with some variation. Then on opposite walls of the sulcus, you will have dipoles opposing each other. And often these inflated visualizations of the cortical surface, you don't really realize that some of these sources are actually quite close to each other. So they might just be a centimeter or a few millimeters apart. So when two dipoles opposing each other like that will cancel each other out if you measure their signals at a distance. So that means the tangential sources along the sulcus here will cancel out, at least almost cancel out. And what's left are the radial sources either at the bottom of the sulcus or at the top of it along the gyri here. But unfortunately, MEG is insensitive to radial sources. So the sources that it can see cancel each other out, and the sources that are not canceled out, it cannot see. So MEG may therefore not see much of this source distribution, even though all hell might be loose here in this part of the cortex. But yeah, MEG is insensitive to some of it, and some of the other parts simply cancel each other out. Well, for EEG, it's also true that the tangential sources cancel each other out, but the radial sources are actually what EEG specializes in. So you will still see those with EEG, either those here at the top of the gyri or at the bottom of the sulcus. So luckily, something is left for EEG to measure. And that's why MEG is less sensitive to extended sources compared to EEG. And this can have practical consequences. I mean, as a rule of thumb, I think the later you are in an event-related potential, the more distributed your sources probably are. So you start with focal sources and sensory cortices, like at the P1, auditory or visual P1, also somatosensory evoked potentials. And the later you are after 200, 300, 400 milliseconds, let's say N400 range or P300 ranges, you probably have extended sources. And these will probably be reduced in amplitude in the MEG compared to EEG. Other examples that I've read about are the supplementary motor area, because this is close to the hemispheric cleft, and it's usually bilaterally active. So you have sources in both hemispheres that cancel each other out, and the radial parts are not visible with MEG. So apparently some authors have reported problems localizing the SMA with MEG. Also, the anterior cingulate gyrus, also an area close to the interhemispheric cleft. If that's active bilaterally, you may have sources that cancel each other out, and what's left is radial and therefore not visible in MEG. So it's good to have an idea of what type of sources you are probably going to get in your experiment and what you are interested in. Look at the literature and see if people have reported preference for MEG or EEG. But if you can, my suggestion always is record both EEG and MEG. Yes, you have to get your hands dirty with EEG. It takes a bit longer, but you can always ignore the data later if you think you don't need them. It's also a good idea usually to compare ERP effects, for example, with existing literature, if you then want to then show your results with MEG. But yes, at least you should be aware of these different properties of EEG and MEG. So there is no simple answer to what's better, EEG or MEG. So you need to know the properties of these types of measurements and see which of these methods is suitable for your particular problem.